Bangladesh, the Vice President of Optica Bangladesh Student Chapter at the University of Dhaka. Welcome to the first day of the workshop on photovoltaic device simulation with Ansys Lumerical. The event has been jointly organized by Optics and Photonics Club of Department of Electrical and Electronic Engineering, University of Dhaka, and the Optica Bangladesh Student Chapter at University of Dhaka. The chapter was first introduced in 2011 and later revived last year in 2021 with an aim to promote optics and photonics research with the help of Optica, formerly known as OSA or OSA. Since our reintroduction, we have conducted several talks, and this will be our very first workshop. Today, we have people tuning in from all over Bangladesh, and I would like to thank you all for joining the event in these difficult times. The workshop will be conducted by Dr. Ahsan Alam, a lead R&D engineer at Ansys. Dr. Alam completed his PhD on solid-state electronics from the University of Alberta, Canada. His fields of expertise include simulation and modeling of solid-state electronic and photonic devices and circuits. As the lead in photonic foundry activities, he collaborates with foundry partners on various projects ranging from PDK generation to ecosystem development. He is also involved in developing Ansys Lumerical system suite and plays the role of a product manager. So it's suffice to say that it's a great opportunity to get to learn about the software directly from him. Great thanks to Dr. Ahsan Alam for taking the time out of his busy schedule to conduct this workshop. I would like to request the participants to mute their mics for now and rename themselves by their real names and raise their hands or write in the chat box if they have any questions. So without any further delay, please welcome Dr. Ahsan Alam to conduct this workshop. Thank you, everyone.
Thank you, Bubbly. And hi, everyone. I hope you can hear me.
Yes, we can hear you.
Okay, thank you. I think thanks everyone for joining and for the opportunity. Really honored to be here and be able to, share some information with you all. And I hope to keep this fairly informal. So at any point, if anyone has any question, please feel free to ask them. We can take a pause and we can talk about your questions. And in terms of the duration of today's session, I think we have a 1.5 hour session. So I am hoping to talk mostly myself for maybe 1 hour or maybe slightly over 1 hour, and then we can have some extra time for questions and answers at the end. But like I said, I think like you don't have to wait until the end. If you have any questions, please ask, and then we can talk about that. Okay, so let me share my screen here, and then we can get started. Okay, so I think the host needs to give me permission to share my screen. Okay, yes. Awesome. Okay, so hope you can see my screen now.
Yes, we can see your screen.
Okay, thank you. Okay, let's get started then. I thought that, for the first session today, we can get started by talking about the Lumerical product suite in general, just because I think like this is an opportunity for everyone to know, what are the tools available and what type of simulations you can do. So even though I know that the focus of today's workshop is on photovoltaic simulations, so we'll talk about like solar cell simulations and look at different types of solar cells and how you can simulate this. But I think like, yeah, at the beginning, we can, talk about the entire product suite in general, just so that kind of like what type of different simulations you can do, and if you have interests on those other fields, then hopefully that's useful information for everyone. So yeah, we'll start with a technology overview. Sorry, these are old slides. So some motivational slides at the beginning, and I don't think you necessarily need it because you're all attending this session, so you're already interested in photonics. But this field is getting excited day by day and generating more interest because of the headline here, right? The photonics is everywhere and growing. And to look at that, like, you don't have to go very far. If you just look at your houses now, everyone has some smart devices in their houses, right? Your TV is a smart TV. Your cell phone has like so many gadgets built in, and all of these devices uses lots of sensors that can use photonic elements. The display is a photonic device where you need to use simulations to make it perform even better. So lots of tools inside your home already where photonic simulations and photonic devices are playing a role. If you go out from your home and look at the industry, there's also so many different sectors where photonics is playing an important role. Internet of Things, chemical and environmental sensing in industries, and so many other technologies are getting used where photonics is playing an important role. In infrastructure and security communications, in 5G, there's a lot of talk around 5G these days, and the key to enabling 5G, that high bandwidth, like photonics would be a critical piece there. It's already playing a critical piece there. And autonomous vehicle navigation is a very hot topic these days. Everybody is interested in that, and that's the future. And the LiDAR that you use in these vehicles, that's also driven by photonics. In the healthcare industry, if you look there, photonics has always been playing a big role there in medical imaging, sensing and diagnostics. And not very recently, that it's been going on for a while as well, but lab on a chip is a very big thing. For like your smartphone also has lab on a chip where it can use photonics to measure your heart rate and your blood pressure and so on. So it's playing a role everywhere. And in the center of all of these things, we have these data centers. All these smart technologies require tons and tons of data, and that's all going through our data center. And the conventional copper cannot keep up with the ever increasing speed and bandwidth need, and photonics has to come in. Fiber optics is needed to transfer the data, and to make the whole communication more efficient, you need photonic circuits to modulate your information on the optical signal. On top of that, there are other emerging technologies as well, AI and machine learning and quantum computing. All of these things, photonics is playing a very important role, and so it's getting more and more important to learn about photonics and explore its different applications. So that's where the tool sets from Ansys Lumerical comes in. So we'll take a look at all the different solvers that are available from our side, and using these tools, you can perform simulations and design your components for various applications. So here just a few topics that we kind of like already mentioned. So datacom, LiDAR, quantum computing, PDK, we haven't talked about this, but like specifically, but all of these photonic devices, or most of these photonic devices, has photonic integrated circuits inside. And so these are, just like electronic circuits, these are photonic circuits built on a chip. And instead of electrons, the signal is carried by light. And so different foundries, just like they offer there's services for electronic circuits. They are now offering services for photonic circuits, and a lot of simulations is needed. Just like you do SPICE simulation for your electrical circuit, you can do photonic circuit simulations and design different components and get them fabricated. So this is also a very important field for photonics right now. We talked about sensing. Image sensors is something where photonic simulation is absolutely essential. Yeah, so we talked about the phones in your hands, and one big thing that gets simulated a lot is the camera on these phones and the lens system, and that's where simulations get used a lot. AR, VR, display, we talked about that. Lighting, metrology and defect. So optical simulation can even be used to figure out defects on the surface of your chip. So there are like so many different applications, and it's all under photonics. So no matter what your interests are in this current world, it's very likely that you'll encounter a situation where photonic simulation is needed. And that's where knowing about these tools that we're gonna take a look at today can be helpful. So this slide kind of summarizes all the different solvers that are available from Ansys Lumerical. Here you can see that the whole thing is categorized in a few sections. So I can just quickly touch on them and tell you what these solvers are about. So let's focus on this segment here. I hope you can see the mouse where I'm pointing. So the section is photonic multiphysics simulation. So this is where we are talking about solvers that allow you to simulate individual components. So for example, the solar cell that we are going to see later today is one example. And so, solar cell is actually a pretty good example, because when you try to simulate a solar cell, you have to consider the optical properties, right? You need to figure out how light is coming into the cell, how it's propagating, how it's getting absorbed. But then also you have to consider the electrical side of things. You have to figure out how electron hole pairs are getting generated, how they're getting collected at the contacts, and if there are losses happening during that transport. So it's a multiphysics simulation requirement. You need to simulate optics, you need to simulate electronics. And that's why the multiphysics simulation suite offers you different types of solvers for different simulations. So first of all, FDTD. This is the most popular product from Lumerical, and I believe a lot of you are probably already aware of this tool. So it's a 3D Maxwell equation solver. It gives you a 3D design environment where you can design your component and run simulations to see how light propagates through your device. And this solver is especially useful when you have devices where dimensions are comparable to the wavelength of the light, right? So you need to capture those effects coming from interference, diffraction, and for that you need a solver that can solve Maxwell's equation accurately. The second solver here, mode, it's actually a combination of 3 different solvers. And this is very suitable if you're simulating, for example, waveguides or optical fibers, where light is propagating through a long distance. The charge solver is our electrical transport solver. This is also a 3D solver. It uses drift diffusion based simulation technology, which is standard in the industry. And this allows you to, for example, simulate the transport of electrons and holes inside your semiconductor devices, like solar cells. The heat solver is next, and this is our heat transport solver, also a 3D solver. And both charge and heat, they use finite element mesh, which allows you to accurately define the geometry of any complex structure, break them into a finite element mesh, and then simulate for charge transport with charge or heat transport with heat. And they both allow you to run simulations either in steady state or transient simulations. And in charge, you can also do small signal simulations. DGTD is a solver that's very similar to FDTD in the sense that it also solves Maxwell's equation. However, the difference is DGTD uses finite element mesh as well. So there are some specific applications where DGTD can offer you more benefit, and we'll talk about that briefly. Next is FEEM. This is a waveguide solver again, but it uses finite element mesh, and it resides with all of these other finite element tools. We have a relatively new solver called MQW, which is a multi-quantum well gain solver. And this can be used to simulate, for example, the gain spectrum of a multi-layered stack. These are very typical and very useful in, for example, 3-5 based lasers or electroabsorption modulators. And then finally, in this category, we have stack, which allows you to easily simulate multi-layered optical devices. So these are about the multi-physics simulation tools that allow you to simulate individual components. On the photonic integrated circuit simulation side, we have interconnect, which is a circuit solver. Well, I guess in theory, similar to SPICE, but it allows you to simulate your photonic integrated circuit, see how light is flowing from one component to another, and perform, figure out the behavior of a big photonic circuit. We also have a photonic Verilog A platform. If you're interested in photonic circuit simulations, then this gives you an alternative way to perform those simulations. And when you run photonic circuit simulation, you need compact models for all the individual elements in your circuit, so that you can do you can include their behavior in the circuit simulation. So that's where CML compiler comes in, which allows you to create those compact models for your simulation. And on the interoperability side, you can see there are lots of topics here. If you're running very large simulations, then you can run your simulations in cloud. And so that's what this first category is about. The automation API is a very useful feature. It allows you to interface the Lumerical tools with MATLAB, or you can hook it up with Python, which is very popular these days. So with the Python API, you can drive all of your simulations from Python, call the solvers, run the simulation, get the results, and plot them all from Python. So this is very useful if you want to automate everything. And then, of course, all the Lumerical tools, they have their own scripting language as well. So even without Python, like you can, within the tools, script everything and make things more automated. We also have tool integration with other third-party tools. So if any of these solvers or tools are useful to you, then you can integrate them with Lumerical tools to run complicated simulation workflows. And on the PDK side, like I mentioned, these days, when you try to create a photonic circuit and you want to fabricate it, you can work with a lot of different foundries. So a lot of foundries are offering photonic services these days. So here's a list of a few of the foundries, and we constantly work with these foundry partners to make new solutions available to users. So that's kind of like a brief overview of all the different tools. Now we can go and learn a bit more about them. So we'll start with FDTD. So like I mentioned, this is our 3D Maxwell solver, and this is the flagship solver for numerical tools. And I have some small video here just to show how FDTD works. So when you solve Maxwell's equation, you can actually see how light propagates through your device. So it's a time domain solver, and it propagates like through the simulation with every time step, and see how light moves from one place to another, how it's getting reflected. And in the end, you can figure out the exact propagation path of your light. You can see all the interference patterns, and see how everything works in your device. So here's another small video. So these videos are also generated with FDTD. So when you run your simulations, you can use a movie monitor to capture, how light is propagating. So some key points about FDTD. It runs simulations at different frequencies. So because it's a time domain simulation, you can use broadband sources, and that allows you to run simulations at multiple wavelengths at the same time with a single run. In terms of material support, we have a material database that provides you with index data, optical index data for most common materials, and you can easily use them to fill up your geometries. And in terms of geometries, we'll look into FDTD today, and you can use small building blocks and connect them together to create any complex device that you have. So here, the picture that you can see is a CMOS image sensor. So you can see it's a pretty complex structure, and this can be built in FDTD. And the great thing about FDTD is that it's been around for a very long time. It has been benchmarked against lots of simulation, measurements by different users. And so we can confidently say that it's highly accurate. And so that's where its main strength comes, that when you're running simulation, there are always questions about accuracy, but because of the fact that it has been benchmarked against so many different simulations by so many users, you can be confident about the accuracy of your simulation. Okay, here's a small success story about one of our users. So Lumotive is a provider of LiDAR solution, and they have used FDTD to run simulations for their LiDAR design. The nice thing that this slide highlights is when you're running a huge simulation, our tools allow you to run simulations in the cloud. And so in this particular story, they were very happy to be able to run simulations on the cloud, which allowed them to run huge simulations, but they didn't have to buy all the necessary computing tools themselves. They could just use AWS and run their simulations and get their designs done very easily. So another cool feature of FDTD that I thought would be very interesting to the audience here is called inverse design. So this is an optimization technology, and this is more relevant to people who are interested in photonic integrated circuits. So when you want to work with a photonic integrated circuit, it comes with lots of different building blocks. And so you have to design all of those individual building blocks manually most of the times. With inverse design, you can actually automate that process. So the name inverse design implies that it's not a conventional design process. So when you design something, you start by figuring out the physics of that device. You figure out what should be the geometry from theory. You do a lot of calculations and figure out a particular base design. You run simulations, see if that's working. If not, then you adjust your design and run more simulations and figure out a final design that works. With inverse design, you don't have to do all of that. You simply tell the solver what your final goal is, what you're trying to optimize, and you provide it with a design space and your choice of materials, and it'll go and figure out a design for you. So for example, these cheese-shaped structures that you can see here is actually a splitter where signal comes in from one side, and depending on the wavelength, it sorts the signal into different output channels. And so you can see how the design evolves. So you start with just a rectangular design space, and the inverse design algorithm figures out where you want to put silicon and where you want to etch it out. And as the simulation progresses, you end up with a very unique looking shape. But from the simulation results on the right side here, you see that it actually works. And it is able to route light on different outputs depending on the wavelength. So here's another example of inverse design. Again, a very interesting looking device. And then you can see that this is also a splitter where light comes in and then it gets split into two different arms depending on the wavelength. Okay, so that was FDTD. Next up is mode. Like I mentioned, it has three different solvers inside it. One is a finite difference eigenmode solver. The other one is a variational FDTD. So this is we call it a 2.5D FDTD. So if you have devices that are very large and you can't do a 3D simulation, you can choose this solver to run simulations much more easily. And then we also have EME here, which is an eigenmode expansion solver, allows you to simulate light as they propagate through very long devices. So the FDE solver is, like I mentioned, an eigenmode solver. It allows you to look at waveguides or optical fibers and figure out the eigenmodes that are supported in these geometries. And then it allows you to figure out the mode properties of those devices. For example, the group index, at what velocity would light propagate through these devices, or the dispersion behavior, that if you're propagating multiple wavelengths, would all of them see the same behavior, or how would the behavior of the waveguide vary or the fiber vary? Bending loss. So when you're using optical fiber, if the fiber is bent, then the property of the fiber changes, and that's something that you want to simulate. So here you can see that if you bend the fiber, then the mode kind of like transitions to one side of the fiber more, and that could include extra loss. Coupling lengths, if you have two fibers or two waveguides side by side, there could be coupling between the optical power through those fibers, and that's something that you want to simulate with this tool. Okay, so next, going into EME, this is, like I mentioned, the eigenmode expansion solver. It's very efficient when you're simulating something long and you want to sweep the length of the device to optimize it. That's where EME is very powerful. So this is an example of a taper where you have two different waveguides on two sides, and then you want to optimize the length so that light successfully transfers from one side to the other. And here is the result of a sweep. So we are sweeping the length of the taper, and then you can see that the transmission is increasing with length, and this allows you to figure out the minimum length possible that gives you a reasonable coupling between the two waveguides. And just for some comparison, you can see that for a structure like this, if you want to run simulations with FDTD, again, you have to do a sweep in order to figure out what length is optimum. For FDTD, if you have these 11 green dots, it takes more than 6 hours, whereas with EME, you can see we did 101 point sweep, and it takes less than 30 seconds on a laptop. So EME is a very quick way to simulate long devices and optimize them. And then the way the workflow works is, once you have your design, then you go back to 3D FDTD and run a single simulation maybe to verify that the results are indeed what you expect them to be. Just FDTD is definitely the more accurate solver. Okay, it's telling me my internet connection is unstable. So yeah, if for some reason you can't hear me or don't see my screen, please let me know.
I think Dr. Alam got disconnected because of some internet issues, so I would request you all to please wait a bit. I think he's going to reconnect soon.
Okay, I think we're back online. Can everyone hear me?
Yes, we can hear you now.
Okay, sorry, I don't know what happened. It just got disconnected from my side. Okay, I don't. Can you confirm like where I actually got disconnected? Let's see. You can still see my screen, right? Or no?
No, we can't.
Okay, I'll share again. Okay. Is this where we got disconnected? Or even from before?
I think we were still in, yes, this one.
We were here. Okay.
Yes.
Okay, so I'll just quickly, okay, sorry, let's start then. I'll just quickly recap maybe the EME one. So EME is used for simulation of very long devices where you want to see how light propagates through the device and you want to optimize, for example, the length of the device in your simulation. So first of all, if a device is very large, running an FDTD simulation can be computationally expensive. And especially on top of that, if you want to do a sweep, that means you're running multiple simulations that can be very time consuming. So that's where EME is helpful as it allows you to do those simulations very quickly. So we have a taper here connecting light from a small waveguide to a very large waveguide. And then with EME, you can see the blue line here. We did a sweep going from, I believe, like 10 micron to 200 micron length with 101 points. And the sweep is very fast, took less than 30 seconds on a laptop. And it tells you, it then shows you very easily that at what length or what minimum length you get a reasonable coupling between the two waveguides. So you can, you don't have to make the device unnecessarily long. That's the whole purpose of this optimization. With an FDTD simulation, if you did it with FDTD, you can see with 11 points, the same sweep will take more than 6 hours. So EME is a way to very quickly optimize these type of devices. And then, of course, once you have your final design, it's always recommended that you go back to FDTD and you run one final simulation, just because it's definitely the much more accurate solver. And you can see that the accuracy is not that off. So it's just kind of like, like a final simulation where you can get all the necessary accurate results about your final design. Okay, so the third solver in mode is varFDTD, which is a 2.5D variational FDTD solver. So this is also an FDTD solver, but the advantage is that it allows you to do 2D simulation for 3D devices. So if you have a 3D device where there's no variation in the vertical direction for your geometry, like see this ring resonator here, where you have a fixed thickness of slab of silicon that you etched to create different designs. In these particular cases, you can collapse this third dimension and convert the index of the material to capture the effect of this third dimension in a 2D simulation. So that's what variational FDTD does. It adjusts the index of your silicon layer, or for example, like the whole vertical stack, into an effective index, and then allows you to run a 2D simulation like this for this 3D geometry. And it can be very accurate, but since you're moving from a 3D to a 2D simulation, your simulation can be really fast as well. So this is used in devices where a 3D FDTD simulation is prohibitive. It takes a lot of time. You can start by doing a varFDTD simulation, which allows you to do a 2D simulation for that device. And then again, once you have done your simulation, you have optimized everything, you can choose to do a 3D FDTD simulation. So here we can see a ring, light goes through, and some of the light couples to your ring, and some of them couples back to the other bus. So in this type of simulations, if you were to do it with 3D FDTD, it takes a lot of memory, it takes a lot of simulation time, whereas for varFDTD, it takes 15 seconds for the simulation to run. So so you can see that, you know, you can, when you're at least in your designing stage or your optimization stage, this type of solvers, varFDTD or EME, where applicable, can be very handy to get you started very quickly. So as I mentioned, if there's any question, let me know. I don't see the question box here. Maybe I'll check if there are any questions there. Okay, I'll just put it on the side in case anything pops up. Okay, so next up is the stack solver. So this is the, no, I believe we have a few other optical solvers still left. Okay, so stack solver, as the name implies, it allows you to simulate devices that has multiple stacks. And so this allows you to perform some quick analytic calculation on large devices, you know, where there's no variation in the geometry on the plane of the layers, but you just have a lot of different layers stacked. And this can be used in the very different applications. For example, here we have an example for a display. And so it's an OLED display, like you can see in, for example, the modern day television. And using stack, you can define all of these layers with their materials and with their thicknesses, and run simulations. Since it's an analytic solver, it's extremely fast. So it happens in seconds. And then once you have done these calculations with stack, you can see you know, how much light is getting transmitted through these layers, how much light is getting reflected, and that allows you to, you know, adjust these layers to reduce reflection, and make sure that, you know, for the different subpixels of your OLED display, you can optimize the light propagation at the correct wavelengths. So here, you know, for example, after the simulation with stack, you can get plots like this, where you can see that, okay, for the different pixels, you are actually transmitting light of the right frequency, and you are rejecting all the other lights for the other filters. And then this particular page also shows that once you have done the calculation in stack, you can actually take those informations to another tool from the Ansys family called SPIOS, which allows you to load those information and run simulations for the entire OLED screen. And in SPIOS, it allows you to also, you know, also simulate exactly what an end user is going to see, which is called, I believe it's called human perception. So this feature actually allows you to see what an user sitting in front of the display would see. And so you start with stack, you get the information about all of these stacks, how light is propagating through them, how light is transmitting and reflecting. You take those into SPIOS, and you can actually simulate your entire display with that other tool. So with Lumerical being part of Ansys now, you know, this is very exciting times for us, because we are doing lots of integration with these other tools, and this is opening up the possibility of more and more applications for Lumerical tools. Okay, I can see there's a question. Okay, so there's a question about FSR. So FSR is called free spectral range. So here you can see that, okay, yeah, sorry. Okay, I can explain. So the question is, what is free spectral range. So you can see that as light propagates through the top bus here or top waveguide here, it only couples to the ring at certain wavelengths, and that depends on several things: the radius of the ring, the index, optical index of the material of the ring, and so on. And so there are some critical or resonant wavelengths where light would couple into the ring, but it won't couple into the ring for the other wavelengths. And so that's why when you look at the light on the end of this waveguide, you will see that light just propagates through most of the times, but for some wavelengths, as it couples to the ring and goes to the other waveguide at the bottom, you see an extinction of the transmission. So these are called resonant wavelengths for this device. And this, you can imagine like that multiple wavelengths can meet that criteria. And so you can see this type of resonant behavior from these ring resonators. And the distance between the two adjacent resonant wavelengths is called the free spectral range, or FSR. So the question was, why was there a difference between the 2D and 3D FDTD? And that's because this is a 3D geometry. So if you simply take a slice of the structure and perform a 2D FDTD simulation, that's not going to work, right? You're losing the behavior of the device because you are not capturing what's happening, that the light is actually confined inside a waveguide, right? It's not everywhere like a plane wave in the vertical direction. And so that's why the 2D and 3D FDTD results are very different, and 2D FDTD is obviously wrong here. The mode solution result is from varFDTD, which is so we call it 2.5D FDTD, just to show that it's different from 2D FDTD. And so in this solution, since we are capturing the effect of the vertical direction by adjusting the index of the material, so you can see that the varFDTD simulation results are in very good agreement with 3D FDTD. So that's the advantage of using varFDTD, that you're still doing a 2D, I'll do air quote here, like you kind of like doing a 2D FDTD simulation, but it's actually capturing the effect of the third dimension as well. And that's why you end up with a fast simulation, but also much more accurate simulation than doing a 2D FDTD simulation. Okay, let me jump to the phone. Okay, so we're looking at the stack solver here. Okay, I think we went through this one. Yeah, just an analytic solver that allows you to simulate stacks very quickly. So now we are going into other multiphysics problems. So we look at charge and heat. So these devices, these solvers allow you to simulate semiconductor devices. So, even though the main focus for our tool set is optics, these optical components often interface with lots of other physics. For example, in electronics, you have signals originally encoded in electrons. And then as those signals come into your photonic devices, you need to convert them from electronic signal into optical signal. And as they go out of your optical signal, you have to again convert from optical signal to electronic signal. So you need to consider the interaction between electrical signals and optical signals in your simulation. When you're doing sensing or photovoltaics, which is the focus for our workshop, in all of these cases, you have to consider not only the optical effects, but also the electrical effects. So the electrical considerations for these devices often can have limiting effects on the performance. In your solar cell, you need to make sure that once the electron hole pairs are generated, they are not recombining a lot, and your current is not getting lost because of that. And so accurate electrical simulation is very important when modeling or designing these type of tools. So the TCAD simulation approach allows you to incorporate these multiple physical effects self-consistently for these semiconductor devices. Now, the heat and charge transport in semiconductors, this is what we are trying to capture with our charge and heat solver. And then some of the other effects that we can capture is, for example, optical charge carrier generation. So this is relevant for solar cells. And then in your electrical simulations, you can also get more insight to the electrical transport. You can get the electrostatic profile for your device, the carrier density concentration in your solar cell or your photodetector or modulators. And all of these information can come out from, say, the charge simulation. So we're going to quickly take a look at some of the applications that you can cover using the charge solver and also the heat solver. So the first application here is modulators. So modulators are optical devices where you control the behavior of your device and how light propagates through it. You control that by applying some electrical signal, and that's how you actually can, superimpose an electrical signal or information on top of an optical signal. So these are called modulators, and these are very widely used components in photonic systems. These modulators can use a lot of different physics. So the most common ones are based on carrier density effects or plasma dispersion effects, where you apply a voltage on a waveguide, you change the carrier density of the waveguide by that voltage, and as the carrier density changes on the path of light propagation, it changes the behavior of the waveguide. And so you can change the phase of the light. You can make the waveguide more lossy by applying a voltage. And with a solver like charge and an optical solver, you can capture those effects and design these devices. The other way of modulating the behavior of the waveguide would be by applying an electric field. So there are lots of different effects that can be used to do that. A Pockels effect is the most common one. You can also model Franz-Keldysh effect or QCAC effects. And with the charge solver, you can actually run simulations on your device and figure out how the charge density is varying on your waveguide or how the electric field is varying on your waveguide. And with those information, you can then figure out how the optical behavior is changing and design these modulators. The other way of modulating the optical behavior in a modulator is by applying temperature changes. And so that's where the heat solver would come in. So with the heat solver, then you would first do your simulation and figure out, let's say if you apply a voltage to a heater, how is the temperature varying on your waveguide? And based on that information, you can then figure out how the optical transport is changing. Okay, so another very popular application field is image sensors. So when you're simulating image sensors, of course, you're going to use FDTD for the optical design. And so you're designing, say, color filters, the micro lens that goes on top of your pixel. You want to figure out that if your micro lens is shifting, if your light is coming at different angles, how the absorption is getting affected by that. And that's something that you will do with FDTD. And then in charge, you will run electrical simulation to figure out the internal quantum efficiency. So you will take the generation rate coming from FDTD simulation. So FDTD simulation tells you how much light is getting absorbed and how many electron hole pairs are getting generated by that absorption. And then in charge, you can actually simulate how those electron hole pairs are getting are moving across your pixel and getting collected at different contacts. So this allows you to simulate the electrical transport, and also, for example, you can calculate the quantum efficiency and also crosstalk. So as light gets collected in one pixel, some of that may propagate into different pixels, and you want to reduce that. So that's why you want to first run simulations and figure out how much crosstalk you have in your image sensor. Okay. Sorry, as we switch, I'll just take another look at the question. So there's another question. Is it possible to design cadmium telluride multi-layer solar cells through FDTD? If yes, how to take doping concentration recombination rates into consideration? Yeah, so I think this question is very timely for the slides that we just saw. So yes, with FDTD, you can simulate cadmium telluride multi-layer solar cells. And so, but like I mentioned, with FDTD, you are gonna capture the optical considerations, right? So you can design your device and try to make sure that maximum light is getting absorbed in your layers. But in order to capture the effects of the doping and recombination rates, that's where you go into charge simulation, and then you'll have to do the electrical simulation in charge, and then that's where you will define your doping profile, and you'll see how carriers are recombining and getting lost from your solar cell, and what fraction of those electron hole pairs are actually making it to the contacts. So you need not only FDTD, but you need charge for the electrical part. Okay, so moving forward. So I think we're leading up to the other optical solvers that we have in our tools. And so this is kind of like talking about some cases where FDTD or FDE, or by that we mean tools that use finite difference mesh can have some struggles. And so when you're doing simulations that require very high accuracy, for example, in optical metrology, like getting a very, very high accuracy with FDTD and FDE can be, you need a very fine mesh for that, and that can require a lot of memory, a lot of simulation time. So it can be very challenging. Structures that require strong local refinements. So the ring resonator example that we saw earlier, photonic crystal fibers, these type of devices, in order to accurately model these holes, you need a very fine mesh here. But because of the way the finite difference mesh works, if you are making the mesh fine at the location of these rings that require your mesh is fine everywhere, and then that makes the simulation very large. Plasmonics, metamaterials, where you have unique structures, complex structures that are carved and not axis aligned. In these cases, FDTD, FDE simulation can be challenging. And so that's where some of the other optical solvers come in. So the DGTD solver, or the discrete Galerkin time domain solver, like I mentioned earlier, again solves Maxwell's equation in a 3D volume, but it uses a finite element mesh. So as you can see, that the trigonal meshes for a 2D simulation case, or tetrahedral mesh for 3D, it allows you to accurately model carved corners and complex structures very easily. And so that's how it allows you to overcome some of the limitations that FDTD and FD can face in certain applications. The DGTD solver has most of the basic features that comes with FDTD. So it has a PEC or PMC boundary conditions. It has the absorbing boundary condition as well, and then block boundary condition for when you're incidenting light at an angle. So it has all the necessary features for most simulations, as well as I mentioned, like the absorbing or PML boundary conditions. In terms of sources, it also has the most common sources. So it has plane wave sources and dispersive material support, or the multi-coefficient material support that we use in FDTD is available in DGTD as well. So let's just skip to the next slide here. So yeah, bottom line here is, in some particular applications where you have very complex geometry and FDTD or FDE, simulation can be very time consuming, or you need that extra accuracy, DGTD can be an optional tool. And so just like DGTD, FEEM is another optical solver that also uses finite element mesh. And so this is similar to the FDE solver in mode. This is also an eigenmode solver, and it allows you to simulate the optical mode of waveguides or fibers. Okay, so next up is our MQW or multi-quantum well solver. And the TWLM here refers to traveling wave laser model. So this is a model in interconnect, which is our photonic circuit solver. And so these two combined gives the user an option to simulate lasers. So yeah, as the slide mentioned, that the combination of these tools allows you to model on-chip 3.5 lasers for different applications. And the way you run your simulation is it requires multiple solvers. And that's where, all the tools in our portfolio comes in. So the waveguide part of your device, you can simulate that with mode or FEEM. And then for the active materials, you use the MQW solver, you simulate the stack and figure out the gain spectrum. And then you go to interconnect and use the traveling wave laser model to create a compact design for your laser. And then for the physical simulation, for the stack, so that you can figure out when you apply a voltage, how much current is flowing through the stack, and how it is affecting the optical behavior of the stack. That's where you can use charge. So with all of these things combined, you can simulate the behavior of these lasers, and this is valuable in different applications, for example, in datacom, in LiDAR, as well as in sensing, because just like you can simulate 3.5 lasers using these tools, you can also simulate electroabsorption modulators that uses multi-layered 3.5 stacks. And these tools or this workflow combination can be used to simulate them. So here is an example of the traveling wave laser model. Let's see. Yeah, so probably not go through the most of the details here. Some of the effects that you can capture using these type of solvers. I can just go through the results quickly maybe. So some of the effects that you can capture using the TWLM model is you can capture, of course, the optical gain, and with the electrical part, the information that you provide to the solver is how much current you're injecting to your gain layer. You can get information about how much loss you're getting because of the radiative and because of the non-radiative recombinations, and then using the gain layer information that goes into the model, you can figure out how much light is getting pumped out of your laser, and then you can figure out your laser output. The model also allows you to account for self-heating inside the layer. So as you inject more and more current in your gain material to get more power, the whole thing gets heated up because of Joule heating. And so the TWLM model actually allows you to capture that effect as well. So finally, when you look at the output, what you can see is as you push more and more current in your laser, the optical power goes up, but if you account for all of these losses and joule heating, you'll see that at high input current, the output power drifts off, and you get less and less power or saturation in your power. So this type of advanced effects can also be captured by using the TWLM model. Okay, let's see. I'm just gonna skip this and then go into interconnect, because I think, yeah, it's almost 9 o'clock your time. So we need to take a look at, let's quickly go through interconnect, and then we can go to the main topic for today, which is solar cells. So as I mentioned, from the component level section, we are now into the circuit section. So interconnect is our circuit solver, and it allows you to run simulations for integrated photonic circuits and optical interconnects. The interface of interconnect looks similar to a SPICE solver, where you have a hierarchical schematic editor. So you have like building blocks for your circuit, and you can have, you know, multiple layers of circuits. So that's why it's a hierarchical solver. And it has an extensive element library that comes with different compact models for passive and active optical components, and different sources and analyzers, so that you can set up your circuit, you can hook it up with different sources and look at the results. It can perform time and frequency domain analysis. The optical signal that flows in your circuit are bidirectional. So you can see effects coming from reflections at the interface between different components. And the simulations are multi-mode and multi-channel. And then finally, once you have your simulation done, there are visualization and data analysis tools that allows you to look at results. When you're doing circuit simulation, you also want to do a statistical or yield analysis, and that can be done by using the Monte Carlo tool. Okay. So this slide shows that interconnect can be used to perform frequency domain simulations. And as I mentioned, you have hierarchical circuits. So here we have a compact model for a ring resonator, but a ring resonator is a very complex device. And so inside it, you can see that you have couplers, you have waveguides. And so with a hierarchical definition, you can define complex geometries and hook them up together to build a large circuit this way. And then with the optical network analyzer, you can apply a signal to your circuit and figure out the spectrum of this entire series of rings that are connected together. And interconnect can also be used to perform time domain simulations. So you can do signal integrity analysis. So here, this is called an eye diagram, and it shows you that when you're decoding the result in your system, in your optical system, how clearly defined your, say, for example, your level 0 and level 1 is. And this opening is very important, because a good opening means that you can very accurately distinguish between your level 0 and level 1. When you have lots of noise in your system or bandwidth limitations, this eye opening can close up. And then that means that you have issues defining your zeros and ones. Okay, sorry, I may have some background noise because my kids just woke up. So yeah, if it's too noisy, let me know. I'll try to do something about that. Okay, so a little bit more details about circuit simulation. The interconnect solver allows you to perform circuit simulations for your photonic integrated circuit, and you can do that by creating compact models of your devices. So here, for example, we have compact models for a photodetector, a directional coupler, a grading coupler, waveguide, ring modulator, or Mach-Zehnder modulators. And this allows you to, take those models and build a circuit in interconnect and run different kinds of simulations. So we know you can do frequency and time domain simulations. When you go and fabricate these circuits with a foundry, you're probably already aware that because of the different variations that happens during the fabrication process, not all of these devices will behave exactly the way you designed them. And from one device to one fabrication to another fabrication, even these individual components will be slightly different from one to the other, right? The grading will behave slightly different for every single fabrication that you do. And the ring will behave slightly different from one fabrication to another. So when you run your simulation, you want to account for these variations and make sure that if you fabricate this device 100 times or 1,000 times, this circuit multiple times, that it'll still perform according to your requirements every time. And so this is where statistical simulation comes in. So with Monte Carlo analysis, what you can do is you can run this simulation multiple times, and every time you can vary the behavior of these components slightly. And that variation information can come in from the foundry because they know their process and they know when you fabricate this, like what the variations would be. And so with a Monte Carlo analysis, you can see that this is a PAM4 device, this particular circuit. And so, well, I guess most of the circuit is absent when it got cropped. But so this particular example shows a PAM4 circuit where you transfer signal in 4 different levels. And by these histograms, you can see that if you fabricate this circuit multiple times, these levels will vary from one circuit to another. And what's critical to you is that even if there's variation to those levels, as long as they're spaced away from each other, then you'll still be able to identify all 4 levels and your circuit will work. And so that's the requirement here, that you do a statistical simulation and you figure out the variations that you see between all those fabrications, and you still need to make sure that everything will work with those variations included. You can also do corner analysis where the foundry will tell you that, okay, if you fabricate these devices with us, these are the extreme cases that can happen. And instead of running hundreds of simulations, you can run simulations for a few corners, and you can see what is the worst case performance of your circuit. And as long as your device works or your circuit works for those worst cases, then you know that it'll work when you fabricate it. So these are some of the tools that you can use when you're doing circuit simulations. So this is the solution with our Virtuoso platform, in association with Cadence. And this allows you to just do the circuit simulation on a different platform by using photonic Verilog A models. And these Verilog A models are generated by the other tool that we have, which is called CML compiler. So as we saw on the interconnect slide there, that when you run simulation on a circuit, you need those tiny building blocks, which mimic the behavior of all of your components, right? Like you need a block that behaves like a photodetector. You need a block that behaves like your grading coupler. And so you need to first, design your photodetector, you design your grading coupler with FDTD, with charge, and then figure out the behavior and create a compact model that behaves exactly like your photodetector or grading coupler. And that can be done using CML compiler. So it's a relatively new tool that allows you to gather all the necessary data for your components, either from experiment or simulation. And then, like we saw, if you want to create a model that allows you to do Monte Carlo simulations, then you need to add some statistical data as well, which could be just that how does the index of your waveguide vary as you fabricate it multiple times, right? So you include the variation of your index or the thickness of your waveguide or the width of your waveguide, that information into the model. Everything goes into CML compiler, and then it gives you these compact models automatically. So you don't have to worry about building those compact models yourself. And so with the interconnect compact models, you can just go ahead and run your circuit simulations in interconnect. And then, like I mentioned, CML compiler can also give you photonic Verilog A models. And then so these Verilog A models can be taken into the Virtuoso platform from Cadence, and then you can run your simulations there. Okay, so I think that was the overview of all the different solvers. I know that a lot of them are not relevant for photovoltaics maybe, but hopefully, this gives you a better understanding of all the different solvers that are out there. So if there are some other applications that's interesting to you, then now you know which tool you need to use for that. Okay, so I'll switch slides here, and feel free to ask me questions about what we've talked about so far.
Assalamu alaikum. Can I have can I ask a question?
Sure, go ahead.
So we are seeing that there are so many simulation softwares, or there's so many what can I say? So many way actually. But is there any dedicated sources from where we can actually learn more deeply about all of this process, like FDTD, DGTD, or EMF, so that we can have deeper knowledge about all of this process and all of these methodologies, and we can apply, maybe we can apply all of the simulations methodology. It's actually there are so many of them, so it's
no, definitely that's a very good question. I can just quickly show this. So if you go to support.lumerical.com, then it'll take you to our support page. And so here, you can register to our website with your Dhaka University or your whichever university you're with. Like if you use your university email ID, you can register on our website. And then once you have registered, then you should have access to these pages. So we call this knowledge base. And so it gives you, information about all the different tools. So here you can see the device suite that we just talked about. And so you can get more information about these different solvers. For example, if you want to learn more about FDTD, you click on FDTD, and then it gives you the reference manual. And then there are so many links that you can, go through and learn more about the solver. And so the top part here of the page, and here you have links to the documentation pages for the different solvers. And if you go down here, then this is what we call application gallery. And so this one contains, different application examples, and we'll take a look at few of them in this workshop. I just searched by solar cell here, and then you can see these are all the examples of solar cell, but you can search for anything here, right? So if you search for CMOS, then you can see all the examples for CMOS image sensors. So this is a very useful page. And then here, you can get information about the different solvers. Also, you can take a look at different examples.
Okay, thank you. I have another question. Is there any prerequisite knowledge that we should learn, or we should have before the workshop, that is software simulation started? Pre-knowledge?
No, I think like for this workshop, it's gonna be pretty basic. So what I hope to do is just talk about the basic requirements of doing a solar cell simulation, and the main goal is to just show the tools, so that if someone wants to go and use this same workflow, then when they open up the tools, like it's not completely unknown to you, and kind of like where everything is, so you can get started. And then when you really get into it and you need more information, then I think like these documentations are definitely a good place to look into. And then like all of these examples, they have explanations, like so talk about the results, right? They talk about the simulation setup in detail. So when you go into the nitty-gritty details, then you have to go into this documentation and learn more about things. I think like the workshops, we just won't have enough time to go into a lot of details. So I think just to attend the 2 sessions, you don't really need any prerequisites. Hopefully, it should be okay to, it should be possible to just follow through and just get the basics. And I think like, yeah, the other thing is that as we go through the different topics, again, if you have any confusion or something is hard to follow, if you just quickly ask a question and we can clarify things, hopefully that'll allow everyone to follow along reasonably well as we go through the different topics.
Thank you so much.
Most welcome. Okay, so we are going into the next section where now we are actually going to talk about how to simulate solar cells. Okay, so when it comes to solar cell simulations, I think we've already talked about this, that there are multiple considerations. Obviously, there are optical considerations, and that is because, like, why would you run optical simulations for solar cells? And so the main case where running optical simulations with FDTD can become crucial is when you're simulating solar cells, you just don't have a block of silicon where you're shining light and trying to absorb the light. You want to make your design efficient, and you want to make your design as small as possible to reduce cost. And so the only way to achieve that is by making enhancements to your design. And like the most common way of doing that is to use some sort of patterning on your device. So some of the common examples would be, you can put nanowire arrays on top of your solar cell, or some patterned multi-patterned surfaces on top. You can even put nanoparticles like gold or silver particles on top of your solar cell to absorb more light into the silicon layer. Or you can even use photonic crystals to increase the absorption. So whenever you have these different patterns that have sub-wavelength structures, you need to use a solver like FDTD because you need to solve Maxwell's equation to figure out how light would interact with these structures and how it will get absorbed. So simulation becomes very important. And then again, the advantage of simulation in general is that it allows you to figure out whether your design would work by just running some simulations on your laptop instead of going ahead and making something that's expensive and may or may not work. So that's where simulation, solar cell simulation becomes important. So with a solar cell simulation, what we're doing is we're doing an optoelectronic simulation. And so in order to do that optoelectronic simulation, we have to use multiple solvers. So the solvers that we're going to use are going to be FDTD. And I think these are all slides. So we used to call our multiphysics solvers device in general. However, this should call for the charge solver now for the electrical simulation, and the heat solver for the thermal simulation. So the three solvers that we're going to use are going to be FDTD, charge, and heat. All of these will provide you a 3D CAD environment where you can design your solar cell and run simulation. And they come built in with a material database that gives you the optical and electrical and thermal properties of the materials. So you don't have to figure out, okay, what property or what behavior should I use for these materials. They would come with the software. And then you get all the physics that you want to capture. Like FDTD would allow you to solve Maxwell's equation for broadband simulation, and that's important specifically for solar cells because you're capturing sunlight, which has a very broad spectrum. And the advantage of FDTD is that since it's a time domain simulation, you can run a single simulation, but then that'll allow you to capture the effect of the entire solar spectrum or the entire wavelength spectrum with a single simulation. And then charge solver will solve the drift diffusion and Poisson equation for the electrostatics together. Can be a 2D or a 3D simulation, and you'll account for all the electrical behavior. So the question that we had earlier about how do you account for doping or how do you account for recombination, like this is where you'll capture for that. And then finally, the heat solver allows you to model the heat transfer. And so in a solar cell, when it's sitting on your roof, for example, like a simple solar panel, it can get pretty heated up as it absorbs the sunlight. and that higher temperature can affect the performance of your device. So sometimes you need to do thermal simulations as well and capture the heating effects in your simulation. So it can be not only optical and electrical, but also thermal simulations could be needed. So with these three tools, we'll see in our examples that you can easily transfer data between the optical, electrical, and thermal simulations. There are built-in tools in these products that can allow you to record the data that you need to transfer from one to the other. Yeah, so we will take a look at these shortly. So this is the simulation workflow. If you're only considering the optical and the electrical effects. So on the FDTD side, you'll do the optical simulation, and the things that you're interested in is obviously the absorbed power, right? How much of the sunlight are you absorbing? And the optical efficiency, which is the ratio of the absorbed power over the incident power. And you want to improve that. You want to design your solar cell in a way so that you're absorbing most of the light. The FDTD simulation will also give you the generation rate, which is how much of this of the incident sunlight is getting converted into electron hole pairs. And then you also get a parameter called the ideal short circuit current density. So if you're doing only the optical simulation, then you don't know anything about the electrical losses. So one assumption that you can often make is, okay, you assume that there's no electrical loss, and so you simply can figure out what is the maximum current that I can get out of this solar cell, which is simply just counting how many photons you are absorbing and how many electron hole pairs does that translate to. And that can give you the ideal short circuit current density. So even with just the optical simulation, you can get an understanding about the maximum short circuit current that you can get from your solar cell, even before you do the electrical simulation. Now, if you want to do the full flow, then you take this generation rate from your FDTD simulation, and then you put it inside charge, and then you do an electrical simulation. When you do charge simulation, then you can get the IV or current voltage relationship for your solar cell. And then you get the actual short circuit current and the open circuit voltage for your solar cell. You'll capture the effects like recombination losses, which can happen in the bulk of the semiconductor or at the surface of the semiconductor, which is much more critical in a lot of cases because these devices are becoming so thin that the surface effects are much more important. And we'll see from our simulation that that's where most of the absorption happens as well. So the surface scattering is very important. And then effect from the contacts. So, you put these large metal contacts on top of these devices. They can have, parasitic resistances. And so you want to account for that effect when you're running your electrical simulation. And then finally, what you can get is the photovoltaic efficiency of your entire solar cell.
Can I have a question, please, Doctor?
Sure.
Thank you for your nice speech. I'm Samiul Islam, assistant professor, Bangabandhu Aviation University. And my question is that you have said that when we want to simulate solar cell, then we are going to use FDTD, charge and heat solver. Can we use stack here? Because in solar cell, we have multiple layers. Suppose we have P-type layer, N-type layer, then some contact layer. Then can we use the stack to model the solar cell?
Yeah, no, thanks, Samuel. Yeah, I think that's a very good question. And then I think like the shortest answer would be yes, you can use a stack because you can use a stack whenever you have a multi-layered structure, and as long as you don't have any variation in the say XY direction. Like if you consider Z is the direction of our stack, then if you don't have any variation happening on the XY direction, then you can actually use stack and figure out how much of the sunlight you're going to absorb in those layers. And stack actually can also give you the electric field profile on your stack layers. So you can take that information and then you can potentially bring that into heat and charge. So there will be some scripting involved maybe, but it is possible. And with that, if it's applicable, then that can be a very quick way of running your optical simulation as well.
Thank you. Thank you very much.
Yeah, no problem. Yeah, no, that's a very good question. And yes, stack is, like, if applicable, it can be a way of doing the optical simulation of your solar cell as well. I think, like I mentioned earlier, that like any other cases, when you're designing, I think stack would be nice. But again, in the end, it's always recommended that you do a final FDTD simulation just to make sure that you're doing a sanity check and checking it against something that's accurate. But yes, stack will give you a good starting point. Okay, so we're going to take a look at one example, and the workflow that we're going to follow here will allow us to account for the thermal effects as well. So here's the simulation workflow. In step 1, we will use FDTD to calculate the optical behavior of our device. In step 2, we'll do a heat simulation to see what is the temperature of our solar cell when it's under operation. And then finally, we'll do a charge simulation that will take the information from the optical simulation, which is the generation rate, and then also the temperature map from the thermal simulation. And then we'll see the performance of our solar cell. So, so this is a cartoon of the device under question. So we have a simple silicon solar cell, just a block of silicon. We have our emitters, fingers at the top, and then a base at the bottom. And like we have an external load connected between the emitter and the base. So the photo generated current will flow through our load, and then that's how we are harnessing the power of the sunlight. The assumptions that we make here is that we first calculate how many photons we are capturing, and then we assume that each photon is contributing to one electron hole pair. And in the solar spectrum, a lot of the spectrum has photons that have energies above the band gap of silicon. And so the assumption here is that any photon that has energy above the band gap, this excess energy gets converted to heat. Right? So part of the energy gets used up to create electron hole pairs, and the rest heats up the solar cell. Okay, so here's a closer look at a cross section of the structure. So we have our silicon layer, and then these are the fingers of the emitter, and then we have the base at the bottom. Now, when you simulate this device, even though in the cartoon it looks very small, it can be a big structure, right? So here we can see that it's a 20 micron distance between the fingers here. So when you try to simulate this device, you can't simulate the whole thing because you're doing a 3D simulation, or maybe in this case, it's a simple structure. So we will actually do a 2D simulation. But still, these simulations can take a lot of time. And so you want to be as efficient as possible. So what we can do here is on the electrical side, you can see that we have 2 emitters and a base at the bottom. We can figure out that the electrical unit cell can be, half of this geometry. Sorry, I think someone's microphone is on, getting some noise. So you can see when you're doing the electrical simulation, you'll take this green region here and then simulate that instead of doing the whole thing. And given that the structure is symmetric and periodic, just simulating this unit cell would be enough. For the optical simulation, we'll simplify it even more because you can see that from the optical point of view, you can just take a simple chunk out of the device, figure out what the optical behavior is, and that should be it. We can just use that to figure out how absorption will happen anywhere in the device. One other thing this block diagram shows here is that wherever we have those emitter fingers, we'll have shadowing effect happening underneath. So we'll simply assume that in that region, like there's no absorption of sunlight. And then with that information, we'll go into FDTD. We'll perform the optical simulation on the unit cell. And then so you can see the input to our simulation would be the geometry, the material property, and then the solar spectrum, because you need to know what the solar spectrum is to figure out like how much of that spectrum is getting absorbed. The output will be the optical absorption. We'll assume that each photon creates an electron hole pair, and then we'll figure out like what is the excess energy that will generate heat in our system. We'll go into the thermal simulation. The assumption would be that the thermal energy from the solar absorption from the optical simulation that will be used as input, and then we'll get the temperature map for the solar cell. Okay, I can see Arpan Saha wants to ask a question.
Hi. I am a second year student from Dhaka University Tripoli. So you have mentioned FDTD on multiple times. Like you're saying that you have to apply the process. Like what is the process? The process of FDTD. Can you
okay.
Can you explain a bit?
Like you mean when we do the FDTD simulation?
Yeah. Like
right. Okay.
You're saying that we apply FDTD. So what's FDTD actually?
Oh, okay. Well, so FDTD means finite difference time domain. So it's a way of solving Maxwell's equation, like a numerical way of solving Maxwell's equation, where the finite difference means that you break down your simulation space into into grids of finite spacing. So in your XYZ coordinate, you'll break down it all in rectangular meshes, and then you'll have multiple grid points in your 3D volume. And for each of those grid points, you will know what material is present there, and then how light is going to behave at that grid point. Then when you run your simulation, so the second part of FDTD is the time domain part. So that means that when you run your simulation, you run it in time domain. So at the first time step of your simulation, you figure out, okay, light is entering my device, and you solve Maxwell's equation to see, okay, how is the electric and magnetic field going to behave at the very beginning of your simulation. And then you go through one time step to another, and every time step you solve Maxwell's equation and figure out the electrical magnetic fields. And once the whole simulation is done, you can go back to your simulation result and then see that as you went through each step of time, how light propagated through your entire device. And based on that, you can then figure out how much of those light got absorbed in your structure.
Yeah, got it. Thanks.
Yeah, no problem. And yeah, so when we go into the actual demo, then you can see how things are set up in FDTD as well. But that's kind of like how the simulation works is you go through different time steps, and then you figure out how light is moving through your structure. Okay, so we talked about the thermal simulation, and then finally, when you go into the electrical simulation, the input would be the optical generation rate from your FDTD simulation. So that's how many electron hole pair was generated. That's going to be one input, and then the temperature profile from thermal simulation, that will be the other input. And then once you run your electrical simulation, you get the IV characteristics like this, and then you get the short circuit current, the open circuit voltage, the output power, and things like efficiency of your solar cell and the field factor. Okay, so I think we are running out of time, so maybe let me just quickly, I want to open up FDTD and show you how this example looks like. So this is the FDTD solver. I'll quickly show you all the critical things. So you have this viewport where you can see the different side views, the X, Y, X, Z, and YZ view of your solar cell. And you also have, the 3D schematic view here, or the perspective view here. So this kind of like gives you a way to see exactly what you're simulating. But the way you make this geometry is from here. So on the top ribbon, you see all the simulation objects that you need to create your design. It starts with materials and structures, which are the starting points. If you go into materials, you'll see we have this material database, and it has all the different materials that you can possibly need. If anything is missing, there's an easy way to add new materials here as well. We won't go into that. But this is the material database where you can see, what are the materials that are available to you. And you can see we have silicon here, which is what we are using for our solar cells. And the next step is the structures. And the way you create your geometry in FDTD is by, combining smaller blocks to create a complex geometry. So you have, primitives like triangles, rectangles, polygons, circles, and so many other types of primitives. You put them one by one in your design tree here, and then those things combined will create, this structure. Here we have a very simple structure. We just have a silicon slab, and then we have the metallic base at the bottom. You can see that we don't have the emitter at the top, just because in the slides we saw that we are just going to take a simple unit cell out of our solar cell, and obviously we are not going to include the emitter, because wherever we have emitter, we actually are going to have shadowing coming from that, so we won't have any absorption anyways. So our structure to start with is very simple. We have silicon, we have metal at the bottom, and now we set up our source. So the sources are added from here. You can see different sources available. For a solar cell, we're just going to use a plane wave. So light is going to come uniformly from the top. And so we set up the source. We'll go into the properties maybe tomorrow, where we have more time. I just want to give you a feel of how things look in FDTD. So you have your source set up, and then you have the FDTD solver region, which is added from here. And in the FDTD solver region, you can see that the geometry allows you to set up the extent of your unit cell here. And then in the boundary condition, what I want to show is here we are using periodic boundary condition on the x-axis, right? X mean and x max are periodic boundary conditions. So this means that even though we are simulating a thin slice, we are using periodic boundary condition on the sides, so that we are saying that, okay, the device is actually very wide. And that's why we can use a plane wave source, because it can just come uniformly down from the top. On the top and bottom of our simulation region, we are using PML boundary condition, which is absorbing boundary condition. So, as light goes through this device, and if anything goes outside, we don't want them to artificially reflect from the top, from the bottom of your simulation or from the top of your simulation. And this is where you use a perfectly matched layer, or PML, so that any light that goes out of your geometry, it'll just disappear into the simulation boundary and not bounce back. So in the FDTD solver, you set up your extent of your simulation, the boundary conditions. And we have this analysis group, which comes from our object library here. In the object library, you see that we have a structure section and an analysis section. And these can offer you lots of different analysis objects. For example, the solar generation rate is available from here. And this is the same thing that we have here. The analysis group is a unique tool. Sorry, where did the property editor go? Yeah. So this allows you to do multiple things. First of all, it has a setup script that allows you to add monitors to collect results. And then it has an analysis section where you can use a script to get the results from the different monitors and calculate the results that you want. So this particular analysis group is already available. So all you need to do is add that, and you can see it will automatically add a field profile monitor, which will capture the electric field profile in your silicon layer, and an index monitor to get the index. And with this information, it'll capture. It will calculate how much light is getting absorbed. It will also use the solar spectrum built in to the script, and it gives you results like the generation rate and the ideal short circuit current and the absorbed optical power. And it will also calculate the thermal power that is getting absorbed as well. So as we mentioned, we calculate, how much of the light, how much of the photon energy is above the band gap, and we use that information to calculate the thermal power that is getting absorbed. So yeah, with everything included, you simply run the simulation by clicking here, and then it'll simply calculate the mesh for the whole thing, and then propagate light through the device. And then as light goes through the device, because it's a time domain solver, you see that the auto shutoff level, which is the amount of light remaining in your simulation, it's going down, just because as time propagates, light is propagating and going out of your system, and so it's just accounting for that. And the way an FDTD simulation typically ends is that we say that, like, okay, when the light has propagated through the entire thing and it has gone out of our simulation volume, we can say that, like, now we can end our simulation. So that's why we keep track of this auto shutoff level, and you can see that it's going down. So I think it should finish fairly soon. Okay, so typically this would go faster, but we've already run out of time. So I'll just quit and save here, just so that I can show you some results. So I just finished my simulation. And so you can, one thing that we can see is that we have this transmission monitor placed at the end of our solar cell. And so we can visualize results like the transmission through the solar cell. And you can see that the transmission is actually very small, right? Because we have this metal block at the bottom. So nothing should typically go in. And then we have this other monitor at the top to see how much of the light is actually getting reflected. And so if we look at the reflected light here, we can see this resonant behavior. And that's because, light is getting reflected from here. As it goes up, it again can get reflected by this top surface, because you have an interface between air and silicon here. And so you can see some interference patterns. But you can see that, for most of the cases, we are absorbing light pretty well, and then the rest is getting reflected. And so that means that, the other part of the light is actually getting absorbed. And where we can see that is in this solar generation analysis group. So we can right click here, and if we do visualize P absorption, so this will give you the absorbed power. Okay, so it's doing the calculation as I did right click, and then so now you can see the absorbed power. Sorry, and then let's see. We'll have to do log scale here, just so that we can see all the different levels. And then so now you can see, this is the optical power that is getting absorbed inside the silicon layer. Again, you can see those interference patterns. So you can see, highs and lows in our absorption. But this gives us, how much light is getting absorbed in this area, because we are doing a 2D simulation, or rather in this volume. And this information can be used to figure out, what is the optical generation rate. So when we ran this analysis group, it also had other results calculated for us. So for example, it's telling us that the ideal short circuit current for this solar cell is a 200 milliampere. And then, this G is the generation rate. So if we visualize this, it shows us, how much electron hole pair are getting calculated. So the unit here is a number of electron hole pairs per meter cube, I believe. So this is how many electron hole pairs are getting generated inside, this solar cell. Again, if we do log scale, you can see that the important thing here is to see that if you look at the magnitude here, you can see we have up to 10 to the power 28 up here at the surface, whereas down here, these values are quite low, right? So you can see that most of the light is getting absorbed right at the surface of the solar cell. And so before, when we talked about, recombination rates, usually you have an interface between surface grown oxide and silicon at the top surface, which can create some recombination centers. And since most of the electron hole pairs are getting generated here, the surface recombination at this top surface can be very critical. And so you need electrical simulations to account for that.
Sorry for the interruption. I have a question here.
Yes.
Yeah, thank you for the permission.
Yeah.
So I want to ask that if we plant a solar cell and we want to see how the light is scattered forward or back scattered, so can we draw a polar plot, and how can we do that? Polar plot.
Polar plots. Yeah, no, it's so like any plot that you have, you can do polar plots. So for example, I guess like, I mean, yeah, this is a 2D simulation. So yeah, it probably won't make much sense here, but yeah, you can, when you plot something, typically you get a line plot, but you know, here you can do like different types of plotting options from here. So if you do a 2D profile of your scattered light, this is where you can choose a polar plot and then see, you can kind of like which, if it's getting reflected in a particular direction, like you see a like a balloon shape or whatever way your light is getting reflected, you can plot that from this option here.
All right.
Okay.
Thank you for that.
Yeah, no problem. Okay, so I wanted to show both the charge and heat simulations today as well, but we ran out of time and actually have to run. So I'm happy that we have a second session tomorrow, so we can continue from here. We'll finish this simple example tomorrow first, and then we'll dive into more complex solar cell examples tomorrow.
I have a question, please.
Okay, sorry. Sure. Maybe one last question, and then we can end.
We are planning to design a new substrate of cadmium telluride. So can you please tell me how do you do that?
Okay, so that's a very general question, right? I mean,
Yes,
can you be a bit more specific? Like
our substrate, let's say we have a silicon substrate over here, the one we designed. So instead of silicon substrate, we want to design a cadmium telluride substrate. So
right.
Which has
so
the,
yeah, I think like the main thing that you need, and correct me if I'm wrong, is you. Yes. Yeah, exactly. But I guess like we don't have cadmium telluride as a material in our library right now.
Exactly.
However, I don't know if you're familiar with this website. I think it's called refractive index.org. Is that correct? Nope, wrong.
I think it's .info.
Right. Okay. Yes. Thank you. Yeah. So this is a very useful website. It has, optical index information for lots of materials, and it actually provides, proper references. And for some materials, it has multiple references as well. So you should be able to, look up the material properties of cadmium telluride here. And once you have, the index data, I'll just go back here. You can easily add, like I was mentioning, you can easily add a material model here. So it's a sample data. Yeah. So we have a material model called sample data. And what you can do here is simply load the refractive index data. Oops, sorry, not 2D, but 3D. So you can simply, load your real and imaginary part of refractive index as a function of wavelength. And you can even import it from different file formats. In fact, refractive index.info allows you to download material data in a certain file format. And I believe in the material database, you can load the data directly in that format. And so you simply have to find your material, download it, load it here, and then you should be able to use it in your simulation.
Okay, thank you.
Yeah, no problem. Okay, so my apologies that I couldn't finish this example today, but we can finish it tomorrow and then continue from there. Hope that's okay. And sorry, I just have to leave.
Yeah, we are way over time right now. I think we should end the meeting and continue tomorrow.
Okay. Yeah. Thank you,
If the
everyone.
participants are okay.
I'll drop out.
Okay. Thank you, sir.
Yeah. Most welcome. Yeah. See you all tomorrow.
Okay, thank you everyone for joining. We will be ending the meeting for now. Let's see you tomorrow.